This is the Hubble Space Telescope, the most powerful telescope ever put into Earth's orbit. It completely revolutionized astronomy, giving us pictures like this of galaxies millions of light years away. So what if you aimed Hubble at the Earth? Someone asked me this recently, and at first I thought it was just a silly question, but then I started researching and fell down one of the deepest rabbit holes I've been in for a while. Because if you actually do the math on what Hubble could see if it was pointed at the Earth, the answer is genuinely surprising. And the craziest part is, the US government has essentially already done this before, not with Hubble itself, but with a secret twin of Hubble built during the height of the Cold War. Along the way, we're going to learn how telescopes actually work, why Hubble can photograph galaxies billions of light years away but can't zoom in on something like the flag on the moon, and what it would actually take to build a telescope that could. The Hubble Space Telescope was created to give astronomers a crystal clear view of the universe by getting above their biggest enemy, the atmosphere. Ground telescopes, no matter how big you build them, always have to look through Earth's air, and that air is turbulent. It is constantly shifting and swirling around, bending light in unpredictable ways. That's actually why stars appear to twinkle. It looks beautiful, but for astronomers, it's actually kind of a nightmare because it makes the images fuzzy. The idea of putting a telescope above the atmosphere was proposed all the way back in 1946, but the technology just wasn't there yet, so we had to wait. Fast forward to April 24th, 1990, and Hubble was launched aboard the Space Shuttle Discovery. It carried a mirror 2.4 meters across, about the width of a king-sized bed, polished so perfectly that the biggest imperfection on its entire surface is just 1/15 the width of a single human hair. That mirror sits inside a body that is 13 meters long and 4 meters wide, roughly the size of a large school bus. The whole thing weighs over 11,000 kilograms. It's powered by these two massive solar panels, and today it orbits 570 kilometers above the Earth, completing one lap every 96 minutes. Now, before we actually get to what Hubble would see if it was pointed at the Earth, we need to understand something more fundamental to how telescopes work, because this is the key to everything. When it comes to telescopes, size actually does matter. A telescope's mirror does two things. First, it collects light, like a bucket catching rain. The bigger the bucket, the more rain you can catch. A bigger mirror collects more photons, which means you can see fainter, dimmer objects. That's how Hubble can actually photograph these galaxies so far away that their light has been traveling for billions of years. Those galaxies are enormous, made of hundreds of billions of stars, so collectively they're putting out a lot of light. Hubble's mirror just needs to be patient enough to collect it, sometimes staring at a single patch of sky for days. But here's the second thing that the mirror actually does that most people don't stop and think about. The bigger the mirror, the sharper the image, not just brighter. Sharper. And the reason why is something called the diffraction limit. When light passes through any opening, including a telescope's mirror, it spreads out a little bit. It's a fundamental property of how light behaves. The smaller the opening, the more the light spreads out, and the blurrier the image becomes. So obviously, the bigger the opening you have, the less the light spreads apart, and the finer details you can resolve in your image. Think of it like a car's headlights at night. When the car is really far away, you can see just one single blob of light. Your eyes can't separate the two headlights. As the car gets closer, at some point the two lights snap apart and you can tell that there's two. That distance where they separate, that's your eye's resolution limit, and a telescope works in pretty much the same way, but with a much bigger pupil, so it can separate much finer details. For Hubble, with its 2.4 meter mirror looking at visible light, the diffraction limit works out to be about 0.05 arc seconds. That is an incredibly tiny angle. It's like being able to separate those two car headlights seen in New York from London. And this is why Hubble can produce such sharp images of space. Just quickly, I get messages every single day from people asking me, how do I get into the space industry? And it made me want to address a common misconception. You don't need to be a genius astronomer or engineer to work in space. Over the last few years, I've traveled the world visiting facilities like NASA, CERN, and ESA, where they are doing cutting-edge research in science, and along the way, I've met people from all different backgrounds. People like lawyers, communications specialists, historians, philosophers, The list goes on. I've known that I wanted to pursue a career in space since I was a little kid, and it's why I went to university and studied astronomy and physics. And that's why I've partnered with Southern New Hampshire University for this video. If you feel trapped in a career that doesn't fulfill you and you've always dreamed of working in the space industry, then SNHU might be exactly what you're looking for. They are one of the largest accredited universities in the US with some of the most affordable online tuition rates in the country. They have programs in mathematics, computer science, really anything that you're passionate about. Making a career change and committing to a passion like this can be scary. SNHU helps to make that easier. The best part is, SNHU programs are really flexible. There aren't any set class times, so you can work when and where you want. I truly do believe it's never too late to pursue a career in something you love. So if this is you, maybe it's a sign. Head to snhu.edu/AstroKobi or simply click the link at the top of the description to explore over 200 degree programs and discover your future. Now let's go point Hubble at the Earth. Being sharp is not the same thing as being able to zoom in on small things. Every time I talk about this topic, I get the same question. If Hubble is powerful enough to image galaxies billions of light years away, why can't we just zoom in and take a picture of the flag on the moon to finally prove those moon landing deniers wrong? This is probably the most common misconception about how telescopes work, and once you understand it, everything clicks. That question confuses detecting something with being able to resolve it. A galaxy might be unimaginably far away, but it's also unimaginably huge, tens of thousands of light years across. So from the Earth, it takes up a decent patch of sky, and Hubble can see it, photograph it, and even resolve structures within it like spiral arms and dust lanes. The American flag on the moon? It's about 1 meter wide. From the Earth, that's an angle of roughly 0.0000005 arc seconds. Hubble's resolution is 0.05 arc seconds, 100,000 times too coarse. The flag is there, but it's 1,000,000 times smaller than a single pixel in Hubble's camera. It's like trying to see a grain of sand on the beach from an airplane. To actually resolve the moon flag from Earth's orbit, you'd need a mirror about 85 meters across. That's almost the length of a football pitch, and that's far beyond anything that we can currently launch. So how big something is in our sky is actually what matters, not just distance alone. Galaxies are big enough to photograph, and flags on the moon just aren't. That's not a failure of Hubble, it's just physics. But we've been getting sidetracked. The question still is, what if we aimed Hubble at the Earth? Hubble sits 570 kilometers above the Earth. Using that diffraction limit that we talked about, 0.05 arc seconds, we can calculate the smallest thing it could theoretically distinguish on the ground, and it works out to be roughly 15 centimeters, about the size of a dinner plate. At that resolution, you could spot individual cars, see the shapes of large animals, make out trees and rooftops clearly. A car would be 13 pixels long, recognizable as a car, but a license plate, that's maybe 2 pixels. You'd see a smudge, but not letters. But here's the thing, that 15 centimeter number is the theoretical absolute best case. In reality, Hubble pointed at the Earth would produce a completely useless image, and the biggest reason is speed. Hubble orbits at 27,000 kilometers per hour. The ground beneath it races past at nearly 8 kilometers every single second. If Hubble took a photo even with a 100th of a second exposure, the ground would smear by 70 meters, completely destroying any detail. To freeze motion at that 15 centimeter resolution, you would need an exposure of about 20 microseconds. That's thousands of times faster than what Hubble's cameras can manage. These telescopes are really slow and sensitive scientific sensors designed to stare at a galaxy for hours. Not action camera GoPros. Well, could Hubble track the ground by rotating? Not really. It would need to move this quickly, but its maximum turn rate is about the speed of a clock's minute hand, far too slow to follow the ground racing past beneath it. And on top of that, looking downwards means looking through the entire atmosphere. the very thing that Hubble was built to avoid. All of that turbulent air between the telescope and the ground would completely blur the image, just like it does for ground-based observatories looking up. And the Earth's surface in daylight is blindingly bright compared to the faint galaxies that Hubble normally photographs. There's a real risk of overwhelming its sensitive detectors. And NASA knows all of this. They have said plainly that Hubble cannot be used to observe the Earth. When they have pointed it at the Earth for instrument calibrations, the result is an intentionally smeared streak, useful for tuning the cameras, but useless as a photograph. Hubble would make an absolutely terrible spy camera, but someone else built a telescope that wouldn't. Now here's where things get really interesting. NASA originally planned a 3-meter mirror for Hubble but switched to 2.4 meters. The official reason was to save costs, but the real reason was the military already had years of experience manufacturing mirrors of that exact size for spy satellites. Starting in December of 1976, the United States began launching satellites called the KH-11 Cannon. These carry mirrors believed to be 2.4 meters in diameter, the same size as Hubble's, but instead of staring at the stars, they were pointed straight down at the Earth. They were designed from the ground up to solve all of these problems that Hubble would have: ultra-short exposures, electronic motion compensation, and the ability to beam sharp digital images back to Earth in near real time. Hubble didn't inspire the spy satellites, the spy satellites inspired Hubble. And we know that they are closely related, because in 2012, the National Reconnaissance Office, the secretive agency that builds America's spy satellites, donated 2 spare 2.4-meter mirror telescope assemblies to NASA, 2 complete, unused Hubble-class space telescopes, just sitting in storage. The astronomy community was rightfully stunned. One of those donated telescopes is now being turned into the Nancy Grace Roman Space Telescope. Before these digital spy satellites, the earlier generations were even more extraordinary in their own way. In the 1960s, satellites called Corona photographed the Soviet Union on actual film. Then they ejected capsules back to Earth that military planes would catch mid-air with a hook as they parachuted down over the Pacific. If they missed the catch, the capsule would self-destruct and sink to the bottom of the ocean. Those early photographs helped to debunk the missile gap, the fear that the Soviets had vastly more nuclear missiles than America. Turns out, they didn't. The satellite photos proved it and arguably prevented an unnecessary and dangerous arms race. So my question is, how sharp are these spy satellites today? In August of 2019, we got an accidental answer. An Iranian rocket exploded on its launch pad, and President Trump tweeted an image of the destroyed site that was shockingly detailed, far sharper than any commercial satellite photo. Within hours, amateur satellite trackers identified that the image almost certainly came from a KH-11 satellite passing over Iran at the exact right time. Analysts measured features in the photo against known structures and estimated the resolution at roughly 10 centimeters. The intelligence community was reportedly furious. Not because the photo was wrong, but because it confirmed publicly what had been carefully kept ambiguous for decades. But even at 10 centimeters, you're still nowhere near being able to read text or recognize faces. A person would be a small cluster of pixels. You could tell it's a human, but not who it is. The classic zoom in, enhance thing from the movies is still fiction. If something is 2 pixels wide in the image, no computer can invent the details that aren't there. It's like zooming in on a mosaic floor. At some point, you just see the tiles. And no satellite can watch a single spot continuously. They orbit the Earth every 90 minutes, spending just a few minutes over any given location. The Hollywood version of tracking a car through city streets in real time from orbit is still pure science fiction. So what if you pointed Hubble at the Earth? The literal answer is you'd get a bright, smeared, useless mess. Hubble is the wrong tool for the job. But the real answer is way more interesting. The same mirror technology, the same optical principles that let Hubble photograph galaxies billions of light years away were developed in parallel and in secret to watch our own planet. Those spy satellites revealed that the feared Soviet nuclear arsenal was smaller than anyone thought. They helped verify arms treaties. They documented the world from above for decades before anyone outside of the intelligence community even knew they existed. And today, that power isn't just in the hands of governments anymore. Commercial companies operate satellites with 30-centimeter resolution available to anyone. During the Ukraine conflict, commercial satellite imagery revealed troop movements and destruction to the entire world in near real time. What was once the most closely guarded secret of the Cold War is becoming ordinary. But the physics that limits all of these systems, diffraction, atmosphere, orbital mechanics, ensures that no telescope, no matter how expensive, will ever give anyone true omniscience from orbit. That same thin atmosphere that makes stars twinkle also blurs the view for anyone looking down. Nature built in a small privacy curtain of its own. And honestly, I find that a little bit reassuring.